Hello students, in this video now we are going to discuss about the quantum numbers. Here quantum numbers are very much similar to the address of human beings. As we are human beings, we are having address in the similar way. The position, energy and distance of the electrons from the nucleus can be designated with quantum numbers. And here actually we get these quantum numbers during the solvation of the Schrodinger equation. So while solving the Schrodinger equation, we use some constants. Those constants here are called as the quantum numbers. Here actually we have here four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. Here first three, principal quantum number, azimuthal quantum number and magnetic quantum number are the constant used while solving the Schrodinger equation. And the spin quantum number is introduced in order to explain the experimental observations. Okay, so anyhow we have the four types of the quantum numbers. Azimuthal quantum number is also known as subsidiary quantum number or orbital angular quantum number. So other two names are also there for azimuthal quantum number. First of all, we go for the principal quantum number. Principal quantum number is designated with small n. It is proposed by the Bohr. It can have any whole positive numbers. That means 1, 2, 3, 4 and so on. Here, but it never gets the zero value. Okay, na? It never gets zero value. From 1 to 3 onwards, it may have any positive integer value. The value of the n here represents the shells which are designated by KLMN and so on. So we can represent the main energy levels or shells of an atom with KLMN or 1, 2, 3, 4 numbers. So here in this picture we can get clear idea how these main energy levels or shells are designated. N is equal to 1 shell is designated with K, N is equal to 2 is designated with L, N is equal to 3 designated with M, N is equal to 4 is designated with N. So like that we proceed. And there is no limit for this number of the main energy levels. We may expect so many number of the main energy levels or shells around the nucleus. Now, principal quantum number helps to determine the average distance of the electron from the nucleus. Here, distance means nothing but radius. If you know the radius, automatically we can calculate the size of the atom. Okay, so the equation to calculate the radius is equal to the Rn is equal to the nx square hx square by 4 phi square m zx square. Nx square h square 4 phi square m zx square. Here n is integer value. It may get the value from 1 onwards. Okay, and h is the Planck constant. M is the mass of the electron and Z is the atomic number, E is the charge of the electron. And here in this radius equation, only two variables are there, N and Z, but other Planck constant, phi value, Z value, my E value. So all these are constant. This one, this one are constants, and already we have their values. That is h is equal to the 6.625 into 10 to the power of minus 27 erg into second, and the charge of the electron in CGS units is 4.8 into 10 to the power of minus 10 ESU, electrostatic units. ESU means electrostatic units. And mass of the electrons in grams is 1.1 into 10 to the power of minus 28 grams. And we know the phi value, that is 22 by 7 or 22 upon 7, otherwise 3.14. So uh, when we substitute all these values in this radius equation, we get this one. Rn is equal to the n square by z into 0.53 angstroms. So here this equation is applicable for all the species which have single electron like hydrogen atom, and this equation is not applicable for the atoms which have more than one electron. So for the what is that, the radius of the first shell of the hydrogen atom can be calculated like this. For hydrogen atom, z is equal to the 1, and for the first shell n is equal to 1. So 1 square by 1, that means nothing but 1 only. So here the radius of the first energy level of the what is that, hydrogen atom is 0.53 angstroms. So like that we can calculate the radius of the main energy level of any shell. Okay, no? So and we may get questions on this in competitive exams, like calculate the radius of the second energy level of the lithium plus 2 ion. So like that they give the questions. Okay, na? And this is very simple method to calculate the radius or sizes of the main energy levels or shells. So as the radius increases, the size also increases. So here principal quantum number tells about the size and radius of the main energy levels. And here principal quantum number helps us to determine the energy of the electrons in the atom. And energy of the electron in an atom is calculated by minus 2 phi square mz square e to the power of 4 by n square h square. Here also the what is that, E is a constant, H is a constant, and M is also a constant. Mass of the electron is also a constant, and we know the phi value, that is 22 by 7. So if we substitute all these values in this equation, what do we get? Means this one. Look here. Here we are taking the units in the we are taking the values in the MKS units. In MKS units, the Planck constant value is 6.625 into 10 to the power of minus 34 joule into second. So like this we take the values and substitute. The charge of the electron in coulombs is in MKS units, that is in the coulombs, is 1.602 into 10 to the power of minus 19 coulombs. So on substituting all these values in the equation, we get this equation. What is that? E is equal to the, yes, z square minus z square by n square into 1312, 1312 kilojoule for mole. So by this equation, so the energy of the first shell of the hydrogen atom now is equal to 1300 minus, so minus 1312 kilojoule for mole. This minus symbol tells us that as the electron approaches the nucleus, its energy decreases. And as the electron moves away from the nucleus, its energy increases. So this can be compared with the behavior of a student in the presence and in the absence of the teacher. So when the student approaches the teacher, he becomes silent, and when he moves away from the teacher, the same student becomes violent. He makes a lot of noise. So like that, when the electrons come close to the nucleus, its energy decreases and it gets stability. And when the electrons move away from the nucleus, its energy increases and it becomes unstable. So here the by this equation, by this equation, now we are able to calculate the energy of the electron in the 1s orbital of the hydrogen, that is 1312 kilojoule per mole. So if this much energy is supplied to the electron of the hydrogen atom, then that electron of the hydrogen atom gets this much energy and leaves the hydrogen atom. When the electron of the hydrogen atom leaves the hydrogen atom, then it becomes ion. So here we can say that this is nothing but ionization energy. So like this, we can calculate the ionization energies also by using this principal quantum number. And we can calculate the energy for the main energy levels of different species by using En is equal to the minus Z square by N square into 1312 kilojoule per mole. Now, the small n value helps to determine the number of the orbitals and the electrons in the main energy level. These equations are known as the Bohr-Bury equations. So, by using the Bohr-Bury equations, we can calculate or we can decide the number of orbitals and number of electrons that can be accommodated in a shell by using the Bohr-Bury equations. Here, Bohr-Bury equations say that the number of electrons, number of shells of nth main energy level can be calculated by using the equation number of orbitals is equal to the nx square, and number of electrons in nth shell is calculated by the equation 2nx square. So like this we have to remember. So these two equations are known as the Bohr-Bury equations. If n is equal to 1, then the number of orbitals becomes 1 square. That means sorry, here I have written wrong thing. What is 1? And if n is equal to 2, then it becomes 4. 2 square means 4. N is equal to 3, then it becomes 3 square, that means 9. If n is equal to 4, it becomes 16. And if n is equal to 5, it becomes 25. So like that, we can calculate the number of orbitals present in nth shell. In the similar way, we can calculate the number of electrons that can be accommodated in nth shell by using 2n square equation. Okay, na? So the number, for example, number of electrons that can be accommodated in the third shell can be calculated by using the equation 2n square. That means 2 into 3 square. That means 18 only. So 18 electrons only can be only accommodated in n is equal to third orbit, third main energy level. So like that, we can calculate the number of orbitals and number of electrons that can be accommodated in the main energy levels. Yes. So these are the some points that we have to remember. And now we go for the azimuthal quantum number. Azimuthal quantum number. Here azimuthal quantum number is also known as orbital angular quantum number, otherwise subsidiary quantum number. It is designated by small l symbol, and it is proposed by the Sommerfeld. The L value depends on the small n value, that means principal quantum number. And here we have the table by which we can come to know the relation between n and L. So for a given value of n, L has the values from 0 to the -1 and its number is equal to the n value. For example, if n is equal to 1, L has only one value, that is 0. And if n is equal to 2, then L gets 0 and 1 values. And if n is equal to 3, L gets the 0 to 0, 1 and 2 values. If L is equal to 3, then the L gets 0, 1, 2, 3 values. If L is equal to 4, then the L value gets 0, 1, 2, 3 and so on. 0, 1, 2, 3 values only. For 4, look here. Here it is 4 and we are having 4 values. For 3 values. For 2 we have the 2 values. For 1 we have only 1 value. Now azimuthal quantum number L also tells about the shape of the orbital. Azimuthal quantum number L value tells about the shapes of the orbital. If L is equal to 0, then that orbital is called as S orbital, and that S orbital has the spherical shape. If L is equal to 1, then the orbital is called as a p orbital, and shape of the p orbital is a dumbbell. If L is equal to 2, then the orbital is called as a d orbital and its shape is a double dumbbell. If L is equal to 3, then that orbital is called as f orbital, and f orbital has the complex structure. In S orbital, there is no slit. We have only single sphere, whereas in a p orbital we have double spheres, two spheres. So that structure is here called as a dumbbell shape. So as the L value increases, the number of the slits increase, and when the L is equal to, the dumbbell is slit in the two directions. As a result, the number of spheres becomes 4. So like that, and in the f orbital, the number of slits is equal to the 8. So like that, as we move on further, the number of slits increase and the shape of the doll becomes complex. So here this is the S orbital. L value is 0 only. So only one value. And for p orbital, L is equal to 3, px, py and pz. And when L is equal to 2, but indicates the d orbital. Here we have 5 types of d orbitals: dxy, dxj, dyj, dx square minus y square and dz square. And here we have the 7 f orbitals. Each orbital has the 8 loops. Each d orbital has 4 loops. F orbital has the 8 loops, and p orbital has the 2 loops, and s orbital has no loops. It has only spherical structure. Azimuthal quantum number tells about the number of the subshells also. So if n is equal to 1, then L has only one value, that is 0. And if n is equal to 2, then L may get 0 and L one value. So number of shells here it is 2. And those two orbitals are S and P. And in it is equal to 3. That means the third main energy level, 3 subcells are there, 0, 1, 2, 3. And the number of subcells is again 7 plus 3 to minus 3 including 0. So in the n is equal to 3 main energy level, we have these 7 subcells, 7 energy levels. LU value tells us the number of the nodal planes also. For S orbital, the number of nodal planes is 1 and 0. For the S orbital, the L value is 0. That means S orbital has no nodal plane. And for the P orbital, L value is 1. So that's why P orbital has the one nodal plane. And we know very well the P orbital exercise the 3 orbitals, that is the px orbital, py orbital and pz orbitals. Okay, and for the px orbitals, xy are the nodal planes. xy is the nodal plane. Xz. And for py, the nodal plane is xz. Sorry, my dears. Look here. For px orbital, the nodal plane is yz, and for py orbital, the nodal plane is xz, and for the pz orbital, the nodal plane is xy. So like that, we can think. We can write the nodal planes. In similar way, for the d orbitals, L value is 2. So each d orbital has 2 nodal planes. And you can for the dx or xy orbital, the nodal planes are xz and yz. And for the xz orbital, the nodal planes are xy and yz. And for d yz orbital, the nodal planes are xy and xy and xz. So like that we can write the nodal planes. And for the dx square minus y square, we have the two nodal planes which lie on the x-axis and y-axis. So these are the two nodal planes for the what is the dx square minus y square orbital. Okay, na? xy planes. So here we can see the different orbitals. This is S orbital, only one S orbital. In any main energy level, we have only one S orbital. And in any main energy orbital, any main energy level, we have 3 p orbitals, 5 d orbitals, 7 f orbitals. Yeah, p orbital has 2 lobes, 2 spheres from the center, and d orbital has 4 spheres. That's why it is known as a double dumbbell shape. P orbital is known as a dumbbell shape, and the shape of the d orbital is called as a double dumbbell shape. And each f orbital has the 8 lobes, so that's why we call it as the complex structure. Okay. Now we move on to the magnetic quantum number. So here this table tells what is that, the number of the subcells present in the main energy levels and the relation between L value and the number of the subcells. Now we discuss about the magnetic quantum number. Magnetic quantum number is designated with M symbol. It is proposed by the Landé. Its value depends on the L value. For a given L value, M value lies from -1 to the -L to the +L. including 0. So for a given L value, the total number of the M values is 2L plus 1. 2L plus 1. Here, for L is equal to 0, M value is 0. For L is equal to 1, M values are minus 1, 0 and plus 1. That means 3. Here only 1. And here is the 5 and here it is the 7. So like that. They become equal to the 2L plus 1 equation. 2L plus 1 equation. 1357. Okay. So like that we can calculate the number of the orientations by using the magnetic quantum number. Actually magnetic quantum number tells about the orientation of the orbitals in the different directions. For example here the orientation of the p orbital is explained here in this diagram. So here mainly p orbital magnetic quantum number tells about the orientation of the orbitals. So, in the absence, actually, here we can understand that clearly. In the absence of electric field or magnetic field, the electron revolves in the plane. The orbital lies in the plane. But when the electric field or magnetic field is applied, the orbital flips in the different directions, so it gets the different orientations. Because electron itself acts as a magnet, no? So whenever it is, and it is a charged body. So when atoms are kept in the magnetic field or electric fields, then the orbitals may get different orientations, and this number of orientations is also quantized. So quantized, and here uh, the number of orientations, that means the number of the different subcells. Each orientation here is called as the subshell. The number of the subcells or orientations can be calculated by using this table. It can be known by using this table. Now we go for the spin quantum number. Spin quantum number. Spin quantum number is designated by S. It is proposed by Uhlenbeck and Gauss. The value of the spin quantum number does not depend on any other quantum number. It is independent quantum number, whereas other quantum numbers are dependent quantum numbers. The spin quantum number has only two quantum numbers, plus of and minus of. Only two values. Here, this plus of indicates the clockwise spin of the electron. Minus of indicates the anti-clockwise spin of the electrons. So actually, the spin quantum number is introduced due to the observations made during the experiments of Stern and Gerlach on the silver atoms. So, in this experiment, Stern and Gerlach accelerated. They focused neutral silver atoms onto the screen, and this beam of silver atom is passed through a magnetic field, and in the presence of this magnetic field, neutral silver atoms split into the two rays and touch the photographic plate in the two different places, here and here. So by this experiment the idea of the spin was obtained, and spin quantum number is introduced. Thank you for watching the quantum numbers. Thank you.